am Rodrigo Obando. I'm a professor at Columbus State University, and I am presenting Introduction to a Unified Model of Cellular Automata. All right, thank you for coming to my talk, Introduction to a Unified Model of Cellular Automata. I uploaded the file, so it should be available for you. And here, it talks about all the different things I want to talk about. So let me go ahead and also talk, thanks to Bob and Todd and some other people. I was, I have a Padlet that I uploaded yesterday, so it's available now if you're interested in looking at all this. So basically, what I'm going to do today is just start with a little bit of the theory, not much, but then highlight some of the functions that are available in the Padlet. So let me start with the detail, the theory of this. They're actually going to be hopefully, working right now with an editor in a Journal of Cellular Automata with a paper where it actually goes a little bit deeper into all the theory, and it's about a 30-page paper. So I'm not going to do that here. All right, so at the very heart of the model lies the decomposition of cellular automata rules into gene functions and simply rules. Each cellular automata rule can be decomposed into k number of genes, where k is the number of values in the cells of the cellular automata. For the case of k equal to 2, which is actually being familiar with, we may express the function that describes the cellular automata like in here. This is f of a sub 0. A sub 0 is the central cell, and then we have a sub 0 naught, g sub 0 plus a sub 0, g sub 1, where g sub 0 and g sub 1 are the gene functions. So any of the rules in a particular for k equal to 2 can be expressed this way. And all the functions, we normally deal with just the entire function. We in fact are interested more in the output of that. And that's how we work with decades. We just looked at the integer. That's the integer that give us the rule, and that's about it. So what I did is I split it. And the reason behind this is that I can actually decompose that in such a way that when I can have a g sub 0 and g sub 1, two different functions, and I say when the cell is sub 0 is 0, there is one gene that is active. When a sub 0 is 1, there is another gene that is active, so I can split it. Now, to generalize that, I actually did that using the Kronecker delta. And for k values greater than 2, then of course now that becomes a summation, of those using the Kronecker delta, like this. And this is the basis for the start for all this work. So when I did that, and then we actually had each one of those functions, the what I call genes. We can start with r equal to 0, the neighborhood, where 0 means no neighborhood. It's just the cell in the middle. So the genes that you have available are just constants, 0 and 1. There are no input whatsoever except for 0 and 1, which is a sub 0. But when you go to r equal to half, which is one cell to the left, this is customary, then we actually have the following genes, which is 0 and a 1, and a sub 1 minus 1 sub naught, and a minus 1. And then if we continue for the next neighborhood, which will be cell to the left, cell to the right, then we now have 16 genes, 16 different functions that we can use. And this, in fact, is the genes for creation of the ECA, or the cellular automata, the elementary cellular automata. Now, using that, we can then have a different way of displaying the set of rules, which is by using a table where the dimensions of the table will be the sets, these gene sets. So for instance, for r equal to 0, this the only 4 cellular automata that can be created. And I know that, in general, they are not really interesting. These are things that we haven't seen. We know that the minimum neighborhood that you need to create something that is interesting, that will have complexity um, or some other interesting behavior, is actually r equal to 1. But I looked at it. So this actually works from 0 all the way to whatever number you want. So this over here is the set of rules for r equal to 0. If we make r equal to 1/2, this is the set of rules. And as you can see, you have up here, you have the actual functions, and here you have the numbers associated with those functions. The same thing that we have down here. These are the functions, and these are the numbers. Now, what you will notice, though, is that in terms of the functions, we find that these 4 functions, of course, they still exist in here, and they are in the relative same position, relatively the same position in the corners. So everything else that is new is actually showed up inside. The problem is that when we refer to those, when we're looking to the integers are different. 5 is not 1, 10 is not 2, because we are expressing those numbers according to the rule space that we're working on. So, but this arrangement, I'm not going to go into the details for that. There is actually a permutation that actually allows me to keep each one of those functions in the same place. Excuse me. So when we do something like this, and then we now express each one of the rules, we can actually create a vector space. And then instead of just having the individual integers, now I have a vector. And the vector will have the gene sub 0 and the gene sub 1 into the vector. So these two will make up 110, 6, 3 will make up 30, 6 will make a 90, that's interesting because 90 is a symmetric rule, actually has both genes are exactly the same. And we can do that also for, this is an r equal to 3, k equal to 3, where you have, a different, a much bigger space. It's a 7 trillion space. So these are the ones that we have in here, and these are the genes. So now for this k equal to 3, excuse me, you have 3 genes. If you go to k equal to 5, you have 5 genes. So this is, the generalization from this. So there is also, this is, by the way, this is the function, the function rule genes actually splits. This is in the Packlet. It splits the rules into its genes. And there is the opposite function, which actually takes genes and it gives you back the rule. So if you provide 10, 7, it will give you 110. If you provide these 3 genes under k equal to 3, r equal to 1, it will give you back this rule. So we can go back and forth in between, and that's at the heart of the whole thing. After that, I use these 2 functions to split them, work with them, put them back together, etc. So when I realized that I could create this transformation, and then I make sure that the functions remain exactly in the same place, relative same space. It doesn't matter how big the space is. The functions that are in one space, they will show up exactly on the same relative space and on the next one. So I used that and said, okay, I can use that position and divide it by the number of rules that I have that, in this case, the primitives. And then I can get a normalized vector instead of just the other one. So in the case of 110, 30, and 90, and 45, these are the normalized vectors. So that will give you the position within the hypercube. It's actually a hypercube. And when you go over here, this function, this says to normal space, it will take the rule and put it into this normalized space. Then you can take those normalized vectors, and you actually get the rules back. So these rules that are actually in R equal to 1, they also exist in R equal to 3.5, 3/2, excuse me. But they do have a different number, as we saw before, because every time that you move to another space, another neighborhood, the rule number changes. So instead, what I can do with this, because they are maintaining the same normalized vector, then I can, if I want to know what is the rule in the bigger space, a rule that I'm looking at in R equal to 1, I want to look at it at, I don't know, R equal to 5 or 7 or whatever. All I had to do is move this into the normal space and bring it back on the new R. And here it is. Excuse me. This is a table for the 110, 30, 90, and 45. And all I'm doing is converting it to the normal space and bring it back under 3/2 or bring it back under 2. And these are the numbers. Of course, if I take those and I grab convert it back to the normal space, they will give me the same number, because effectively it is the same function, but we never seen them that way. When we treat them just as integers, they are just different integers. By using this normalization, now they remain in the same place. And now I can say, instead of, I'll tell you, I said, about that rule 110? And I said, yeah, I know, I've heard of it. Yeah, okay. Have you heard of the 28,270? No, I never heard of that one. Well, it's the same thing. It's just in the next space. Well, instead, I can just say, do you know about the 1/5 and 8/15? No, that's in the quiz at the end, by the way. But if you know about that one, do you know what that is? And this one is unique. This identifies that function, that cellular automata, regardless of the neighborhood. And that, to me, was actually very useful. So that then allows us to define what we call the canonical rule. The canonical rule basically says, what is the minimum range of value of R under which we can realize a particular normalized rule? So in the case of this, when you take, this one, you take this one to normal space, it's just, well, of course, 110. We make it here in R, we then take the canonical rule, and it gives me, it's a 110 K2 1. So I can identify that. So if you find an interesting rule in some space, you say canonical rule, and then will actually give you what is the minimum space where that rule exists. Where did it show up first time as you're going up? So in this case, the minimum value of R for the rule, whatever, 1 billion, et cetera, and K2 R2, it's actually 110, and I chose that, because I knew what it was going to be. But you can do this with any of those, and then you'll be able to know, what is the minimum value of R. So this one is another one. I just selected this one, and then you say that 3 and 1. This is the normalized rule, and then it gives you back the same rule, which means this is the minimum value of R under which this particular rule exists. Excuse me. So also that then allows us to create what is called a Symmetry Index. Back when we started working on this, and I think it's talking about probably in the 90s when they started discussing these things. For K equal to 2 and R equal to 1, we define symmetric rules. They were perfectly symmetric. We also define semi-symmetric, which is sort of, one side was symmetric, another side was not. And then totally, asymmetric. So there was no symmetry at all. Now, when we work with rules for the K is greater than 2, we end up having that this characterization is too broad, because now the part that is semi-symmetric rules are, much wider, and there are different levels of semi-symmetry. And what I defined, I said, okay, we define a symmetry index sigma for it's S over K, where S is the number of symmetric genes in the rule, divided by the number, by K, which is the number of genes, or and in this case, the number of values in the rule. So we have this, so there's the function that says the symmetric index. We just take, different rules under the, we find the symmetric index for each one of those. And I even tried to this one. This is in K for 7 in R1. So that's a little bit bigger. I didn't memorize it. I tried, but so here we have, this is the symmetry index. For instance, 110 is 1/2. That's semi-symmetric. 30 is also 1/2. 90 is totally symmetric. Symmetry index is 1. For this other one is also 1. For the next one is 1/2, 1/3, 2/3, etc. So this particular concept actually made it to me easier to then generate random rules of various levels of symmetry, because all I have to do now is I work for the genes, and I make sure that I create or find genes that are symmetric or not symmetric. And I said, I need 3 out of 5, that will give me a 3/5 symmetry index. And then I can do something like that. So these functions are in there. So if you want a random symmetric rule and whatever K with whatever R, you just ask for it and then it will give it to you. And you want an asymmetric rule, the same thing. You want a semi-asymmetric rule, it will do that as well. Okay. So there is something also that I found. I'm not going to go into the details for this, but there is a way that you find equivalency between 2 different rules, and these 2 rules are actually they are equivalent to each other, except that they are shifted, right? The colors are shifted, the output is shifted, and in this particular property, we normally know it as a complement rules in the K = 2. So for instance, we can find the Modulo-Additive Equivalent rule for 110, and this is a 1, this is the shifted, is shifted by 1, which is 137. For 30 is 135, for 90 is 165. So this is what we normally have seen that as a complement. So 110 is actually 135 as a complement, or in my case is the Modulo-Additive Equivalent rule. Why is it that I call it that way? Is because when you go for K greater than 2, you no longer just have the flipping of the colors, but you actually have the shifting of the colors, which it happens to, of course, the subset of that is the complement in K = 2. So this rule, for instance, with respect to this rule over here, is every cell, every output is just shifted by 1. But they are identical. And this one here, this is separated by 1, this is separated by 2. And you can do that in any other space. You can find, you say, oh, this is an interesting rule. So what is this one shifted, 2? This is, in the paper, I have it defined as a C modular additive equivalence. So it is equivalent by shifting by a C. By a C value. So the interesting thing is that in order for me to do this and actually find the shifter rule, all I have to do is take the rule from the normal space, move it over to the normalized space, rotate the values of the vector, and bring it back to normal space, and voila, that's the shifter rule. So there are many operations that actually become easier to do on the normalized space that were kind of a hassle when you work on the regular space. All right. So that also allowed me to then start creating some other things, and I was having so much fun when trees became available, because before that I was doing some other ones that it didn't look as pretty. So I created something that I called the genetic trees that basically take a rule, split it into the genes, and then those genes will be also into genes, etc. Because remember that since one space is contained in the next bigger space and the next bigger space, etc. So if you take any of the rules from any of these spaces, the genes will actually be functions of the previous or of the smaller space, so on and so forth until you get all the way to the end. So in this case, you can see that a genetic tree for 110, again, is 10-7, and each one of those genes is actually composed of, in this case, constants 0, or no, not constants. There is a constant, but there's another one that is not. And this is rule 30, which is 6-3. This is 90, which is symmetric, remember? There's gives you the Sierpinski triangles. It's actually composed of exactly the same genes, on those sides. And then this is the genetic tree for 75, which if you see this is just the swapping of the two genes in here, But then that not only allow me to do that, well, I can do that, of course, in a genetic tree for a bigger rule. I didn't want to put another one that was much bigger because I tried these with K equal to 23, and they're just huge trees. So along the same lines, I actually created the equation trees. The equation trees is simply using the genetic trees, and I'm using some of the functions in trees that I can apply a function, to the entire tree, and it will apply to all the nodes. So here's the equation tree for 110. These are the equations that are actually used for each one of these. Again, here's the same equations for these two, etc. This is one for equation tree for this one, which is much bigger. The way that this works, I'm just taking the genetic tree, and then I apply the rule equations and gene equations, so I can get those. On top of that, I got another one, which is the CA evolution tree, and this is for 110. This is the evolution of 110, but this is the evolution of its genes and each one of those. Unfortunately, and I think I need to find the new functionality in terms of the trees, because they're getting to be too big. Whenever I actually call them, they are all clustered together, and I need them to be a little bit more separated. So on top of that, there are also canonical trees, normal trees, monotone Q trees, and symmetric index trees. Then there are all kinds of special functions, identity rule. You can actually get the identity rule in any of the spaces. So this is for 2, 1, 2, 3, 3, 1, and 4.5. And these are the different identity rules that you can realize in the different spaces. The gene rule, that's another, another one of the rules that I have in here. A gene rule, simply what it does, it takes a gene and it places it in a particular gene of a rule. And then you can indicate that right in here. You say, I want 13 to be placed on the gene number 1 for 3-1. And then it gives you that. If I actually do the normal space of that, you can see that the other parts is 0, but this one here has that gene. 13 is actually 12/13 in the normalized space. So as you can see, identity rule in this normalized space is 0, 0, 0, 0. The vector 0 is always it gives you the identity rule when you bring it back from normalized space. The reflect rule, actually, if you have a rule, basically what it does, it takes the rule, then it gives you the reflection of the rule. There are also test functions. Can test for monotonicity, symmetry, reversibility test, reflection test, etc. There are some other various functions such as Langton's Lambda parameter. There is also a new parameter that I call delta. There is a rule splice in which you can take a rule from one space and splice it into a bigger rule. And so in this case, what I'm taking is, I'm taking rule 110, and I'm placing it under in the identity so that that's the only thing that it has, but in k equal to 3, and then uh, I just show it in here. And as you can see, it looks just like what it is. It's 110, but realized in a bigger space. And of course, the other part in this other rule is inert. It's not doing anything. So this is a splicing of genes from one space into another space. And I actually done this. I put 110 on one side, and then I have the reflected on the other side. Then I can actually use um, the additive equivalent, and then modulo-additive equivalent. Then I can actually have the two rules in the same rule. I've done that with a space of k equal to 4, so that I can put all the two side by side. As you can see here, this is the equation for that. This is the equation without doing it through Boolean function, which is in Wolfram, Wolfram language. And these are the two equations for that. They don't look anything alike, but they actually behave the same. So anyway, so the conclusion is, I think I'm providing a sort of organized way of actually exploring cellular automata in a way that I don't think that we've done in the past. Providing a uniform and unified model where we can now move things into a normalized space, do all kinds of operations there, bring them back, which makes it a little bit easier. And that's, I think, all I have the time. And the Padlet will be updated. It doesn't have a lot of documentation, but I will be doing that as soon as I can. Thank you very much.